Okay, let's talk about this device. This is called um, a Fusee clockwork device. This is kind of an old um, mechanism that goes back to probably I think the 1700s. Okay, maybe even earlier actually. It was discovered, I think, around the 1500s, and they don't know who actually originally invented this. So some brilliant high IQ mind figured this out, more than probably 500 or 600 years ago. This video is about a gravity electric project that I've been contemplating for many, many years and circling back to it now. Now, today we're going to talk about this device right here because this device is potentially going to be part of my gravity electric project that I'm working on. Now, my device eventually, I guess I'll call it a poly mechanism. We'll get into that, what that term actually means later on, probably not in this video, but what we're really after here is what is the end result? The end result is to produce electricity using gravity. Now, I'm not the first person to ever come up with this idea. Wow, what a surprise, right? But I have an approach that I think is gonna work really well. Okay, but initially we need to talk about how are we going to generate this power. There's all kinds of power sources out there, right? You got nuclear, you've got solar, you got wind, you got hydroelectric, you've got ocean currents, right? Or ocean waves. They use this to generate electricity. There's through like buoy and floats. There's all kinds of really cool ideas out there. So this is a very old school approach, and we're going to talk about this device here called the Fusee, I believe it's pronounced. Probably not pronouncing it right. It's a French word. Now, it's very unique. Inside this drum here is a spring, a tightly wound flat spring. It's all inside there, really tightly wound, right? And one of the big challenges about springs is as they unwind, they begin to lose their torque value. When they're wound up really tight, they have a specific torque value, and as they begin to loosen or unwind, they slowly lose their torque value. Now, this is used primarily in clockwork, okay? And that's what we're looking at here. You can tell there's some other gears here. Eventually, this spring that's in this barrel, drives this particular pulley-looking device here, which drives other gears, which eventually drives the hour hand, the minute hand, and maybe possibly even the second hand on a clock, right? Nowadays, of course, we use solid state electronics to tell us the time, right? We don't use this kind of technology that much anymore, which is kind of sad because it's really cool. Classical or classic mechanics is a part of physics, and for me in particular, I find this area of study fascinating. I also think it's very applicable, okay, to the energy crisis, and the search for how to use energy better. So that's how this originally came about. It was an effort to build a clock. Now, as I mentioned earlier, when you have a spring, as it unloads and unwinds, it loses its torque. Well, the age-old problem is, how can you use it for generating a clock? If it's losing its torque, it's going to not be consistent in the way that it conveys that torque or that power to provide precise time, right? So what would happen over a day is the clock would begin to lose its accuracy. But somebody in the 14 or 1500s or even earlier designed this particular conical device, and what it does is it compensates for the spring being unloaded. I mean, it's absolute genius. You can see there's a gear obviously here attached to this right there. So it's got teeth and a gear. But this is this is a rope. In this case, it's a chain. Okay, and it goes around and around and around and around and around and around. And the inventor realized that as the torque in the spring is unwinding, you just increase the diameter to compensate for the difference, and it actually works wonderful. It keeps very good timing. You might lose a few seconds a day, but there are ways to adjust for that over time. Usually it's seasonal temperature changes and stuff like this. You make a couple changes, very minute changes, and you keep in great timing. I have a pendulum clock coming in that I bought, and when it comes in, we'll do a video on that, and I'll show you. That's another way you can run time, is through the pendulum and escapement mechanism. Okay, this has an escapement mechanism too. It's here in the background. Okay, but this uses this coiled spring rather than a pendulum and a weight. They're both excellent designs. They both keep really good time. The reason I'm looking at this one is because this is very compact. This design is very compact. It uses very little space, and it's very accurate. Now, my concern is not so much keeping time, but using the power that this spring has in a compact format, or a compact form, which you can see this is very compact, right? Okay, so I wanted to introduce this particular device called a Fusee device. It consists of a spring barrel with a spring in it, a highly tightly wound spring, and the Fusee pulley system that goes along with it. Okay, and of course there's some other gears and stuff like that going on. Okay, all right, let's switch over to a video. I want to show you something. Well, let me show you another picture, and then I'll switch to a video. Now, here's a gentleman that is called 4 wooden clock escapements. It's just some guy that did 4 different types of escapements, and this is one of them we're looking at. But what's unique about this particular gentleman's approach is, if you look at this, there's a rail system here, right? This is called 20 by 20, I think, aluminum extrusion. Okay, that's what this stuff is here. This black thing here and this black rail here. What's really cool about this is you can put bearings in there, slide them in. You just use bolts that fit down inside there, and you screw them tight, and it'll hold whatever's in place. In this case, he's using some aluminum jack shafts with bearings and some pulleys with these belts. These belts are used a lot in like CNC machines and what do you call these machines? These 3D printer machines. They use these kind of belts for precise movement in their CNC operations. He uses it. This is like a 60 tooth belt, and then you can't see, but behind this belt back here is a little 20 tooth belt, and then on the same shaft is another 60. Then this belt goes like this down to a 20. There's a 20 back here, and then he has this huge pinwheel. Okay, and there's an escapement mechanism and stuff like that that's associated with this, and he runs this whole clockwork using this system. And you can't tell very well, but there's a string right here, and it's tied to this little pulley, and it's hanging down right there. See the string right there? It's hanging down that way. Okay, there's a string hanging this way, down like that, coming off this pulley right here. Okay, and that's how he drives the system. It's very ingenious. The reason why this is I may incorporate this is because you can quickly, in a matter of moments, set up your pulleys and your belts and get your tension right and just lock it down. Very, very convenient. Now, I don't know if that'll work with really high tension, but it works with medium and low tension pretty well. High tension, these bearings could potentially move in the rail if they're under a really high load. So we'll see if it works, but this is pretty cool. Very simple approach, easy, quick setup. I really like it. So this may get incorporated into what I'm doing. All right, let's look at a video. I'm going to show you something about the Fusee device. Okay, so that's how the Fusee device works. You can see that the spring inside this barrel, right? We just watched it. The spring inside that barrel is releasing, and it's pulling this pulley, right? This multi diameter pulley, the Fusee pulley. Now, normally he's just unwinding it real fast, right? He's just unloading the spring in there. Okay, but normally there would be an escapement mechanism and gears and other things associated with this that would keep it, tick, tock, tick, tock. It would unload really slow, just like old-time mechanical clocks. Okay, and that's a very attractive way of controlling the unloading of a spring. Okay, and we can leverage this, and we can potentially use the spring at higher spring load rates to get higher torque to do some pretty cool stuff. Okay, the rate of the torque inside this barrel is pretty low, right? It's just driving a clock with really light set of gears and really light hands on a clock. You don't need a lot of torque to drive this clock, right? But for gravity electric purposes, we're going to up the game here. Okay, use this very similar type of setup, but we're going to drive the torque up higher. So let's go switch over to something else. I'm going to show you that, how we have to calculate. One of the first things we got to do is we got to calculate the kind of torque that we need. Okay. All right, here we're on a spreadsheet. I'm not going to spend too much time on this because a lot of people get bored with the math, but we're going to talk about this a little bit. It's really important that we understand how to calculate the necessary torque using, that's called a flat spring. Okay. And I'll just go through this kind of quick. Up here at the top is called Young's modulus. This is a series of attributes, right, or variables that we plug in, and eventually we're going to get a number at the bottom here, the torque that we're after. So the first thing we got to do as part of this equation, this is basically a lesson in physics, okay, in classical physics. We need to know Young's modulus basically effectively measures elasticity. Think of a rubber band. If you stretch it and stretch it and stretch, eventually it'll snap, right? That's elasticity, right? Everything has some type of elasticity. Branches in a tree, even nails, everything. They may not seem like it, but everything can be stretched. And there's a way to measure that. We use it called Young's modulus. Okay, you'll notice in here I've got this thing, I've got a little description here called most steel. Well, that's most steel, carbon steel, stainless steel has this modulus value, 190,000 Newton meters squared, newtons over meters squared. Okay, yeah, I'm using metric, and we're gonna convert it to U.S. value, imperial, I guess it's called, as we go along. All right, so most steel has elasticity of 190,000 Newton over millimeter squared. I'm experimenting with different material dimensions. So just for now, I have material width of 12 inches here. You can see 12 inches. It's converted, millimeters to inches, or inches to millimeters, sorry. It comes out to 304.8. That's the width of the material. Yeah, pretty wide, right? It's a foot wide. The thickness, right now I have it at 1/16 of an inch here. That's the millimeter conversion. The length, which we calculate using a nice little calculator there over at one of the, I think it's National Watch something organization. Anyways, for the Fusee spring, there's a way to calculate it, and they have a calculator there. So anyways, at the moment, mine's 898 inches, converts to this crazy 22,809 millimeters. And then we get a spring constant. We need the spring constant. This is 846 and approximately half newtons times millimeters over radians. Okay. This gets converted to Newton meters, 5.32. And we can convert that to pound feet, which is what we want in the US, 3.92 pound feet. Okay. And then this is the real trick here. That's for 360 degrees, right? That's how much torque we get by turning that spring, that flat spring, one full time, 360 degrees. But the cool part here is we can turn it multiple times, right? We can turn the spring once and tighten it twice and 3 times. We can keep tightening it up, right? Tighter, tighter, tighter. That's what's happening inside that Fusee barrel we looked at earlier, right? So you can put the number of turns here. I got to calculate it, and we get It's really just this calculation times the number 5 and bam. So at the moment it's 19.6 pound-feet. All right, so for an example, I might do something like, I might change the thickness of the material. Let's say I put it at 1/8 of an inch, which would be pretty thick. Also, we have 156 pound-feet, right? So just changing wherever you see orange here, light orange, changing any one of these dimensions will give us different numbers, like 8 inches wide reduces the pound-feet to 104. Okay, instead of 12 inches wide, right? Maybe we get 7 turns out of that thing. Now we're up to 219 pound-feet. Okay, so these are all things I'll be experimenting with to determine, how much torque can I realistically get out of like a 1 foot or 12-inch cylinder, right? So this is a very, very important calculation. We're actually starting on the end. We're not going to design something and then get surprised at the end. Oh, wait, I miscalculated. We got to calculate torque. We're going to I'll set up all the gears and figure out, okay, if this torque goes through X amount of a gear train, what's the torque at the end? Because the torque's going to be reduced as you go through a gear train, right? You can either multiply the torque or reduce the torque. In our case, we'll be probably reducing the torque. Maybe not. We'll see how that's all going to work out. But so this is the critical first stage, is to figure out, how much torque can we realistically generate? Is it realistic to have an 1/8 of an inch thick steel? Probably not. It's pretty thick. It'd be really hard to make a spring out of that thick of material. Even this, at a 1/16 of an inch is going to be pretty difficult. So these are things that have to be thought about. All right. So I want to introduce this kind of beginning stage as I'm getting re-engaged into this project and share with everybody the plan to move forward. And I'll be talking more and more about this as we move forward. For now, that's it. Talk to you all real soon again next time.